Hey everybody, it's been a while since we've done a lesson, but today's lesson is going to cover functions and relations and what makes a function, what makes up independent values, what makes dependent values, all those good things that relate to section 4.6. Okay, now starting off with 4.6, and sorry, this course kind of takes a step way back into chapter 4, which you've probably skipped when you were in 0481. But the section 4.6 is just kind of an introduction to functions. And it goes over what a relation is, what a function is, and domain and range. What I have here for a relation is that each member of the domain, X, relates to at least, and I have that in different color there, at least one member of the range, which are your Y values. So I would say basically everything that you see on a coordinate plane. You know, when I talk about a coordinate plane, you're talking about the X and Y. And any point, if you put a point here, if you put a point there, as long as you put a point somewhere, it can be even on the axis itself. If you have a point on the coordinate plane, you're talking about a relation. So everything that you're going to see, I think, in this entire section in 4.6 is a relation. I don't want you to think that the opposite of a relation is a function, because that's not true. Because some people say, well, if it's not a function, it's a relation. If it's not a relation, it's a function. No, everything is a relation. We just have to determine if it's a function or not. You know, everything that you're going to see is a relation. So like I said, the opposite of a relation is not a function. The opposite of a function is not a relation. It's just that all functions are relations. But are all relations functions? Not quite. Now, the thing that you might want to notice from the definition of a function is that it says each member of the domain relates to exactly one member of the range. So that means there's a one-to-one relationship. There's only one X value. If you ever see a repeating X value, let's say you have ordered pairs like 1, 7, and then we have another one that's like 2, -3, and then we have 1, -4, something like that. Well, we have repeating X values right here. We have a couple ones. That would not describe a function right there. And I have a good way of kind of describing, especially a real life example for describing what makes a function what it is. And then right here, the domain is all the X values. It's the inputs. And the range are all the Y values, the outputs. Okay, now this isn't in your notes, but I just wanted to, in class, I usually go over this, which I always thought was a good example or a good analogy of what makes a function. Let's say you are the owner of that vending machine. Okay, so you want a vending machine that is functioning. That means it's giving out a product and you're making a profit. You want to look at this from the vending machine owner's point of view. So and I'm sure everyone understands how a vending machine works, but let's say you wanted to get that bag of chips right there. Those look like Lay's baked chips or something. But you want to get those. And so those have a value on the machine of A5. Okay, so you go through and push all those buttons, A5. And then bonus, all right, that's going to come down. But then whoever coded this machine made this entire row A. So that's going to come down. And that candy bar looks like, or granola bar, is going to come down too. So you're going to, bonus, that's a jackpot for you at the vending machine. And whoever coded this machine made some huge errors because they made 3 different rows A. So that is not going to work out well for you in terms of making money. So that would not be a functioning vending machine. So we need to fix that vending machine by assigning different values. Let's say we can call that maybe E, and because we already have a C. But let's say we call that right here, let's call this F. So then whoever coded or programmed that vending machine can go through and now make it work so that when someone picks A5 or whatever sequence letters they want to put in there, only one thing is going to drop down. Okay, so for this first example right here, we've got to identify the domain and range of each relation and determine whether each relation is a function. The domain is equal to, I see a 3 there, I see a -4, and there's another 3, so I'm not going to repeat it, and I see a 6. The range is, I see a 1, there's a 2, there's a -7, and there's a 4. I should really put those in order. -4, 3, and 6. That's the domain. And the range is -7, 1, 2, and 4. But more importantly, is that a function or is it not a function? And it's, like I said, it's just a simple test of looking at the x values. And if you see any repeats, then it's not a function. If you see only one x value and that x value does not show up again, I see a 3 and there's a 3 there. So when you have those repeating x values right there, this is not a function. Is it a relation? Yes. Not because it's not a function. Everything that you see on this page is a relation. 1, 2, and 3. They're all relations. There's no question about it. The question is that relation a function? And that one is not a function. Same thing right here. Let's list the domain out. Let's try to put these in order right away. So we've got the lowest value is 0. And then we have 2/3. That's a member of the domain. We have a 4 and 11. And the range is just all the y values. So the y values are going to be -2, -3/4. We have 4, and we have 6. And most importantly, are there any other 4s? No, I don't see any 4s in the x spot, I should say. I mean, I see a 4 here, but that doesn't matter. Is there another 4 in the x location? No. Is there any other 11s as an x? No. Are there any other 2/3 as an x? Nope, that is not going to be there. And is there a 0 as an x? And that's not there either. So this is an example right here that is indeed a function, because every member of the domain relates to exactly one member of the range. 4 only relates to -2. 4 doesn't relate to, there's no 4/6, there's no 4/4, there's no 4 -3/4, that's it. All right, for number 3, you've got an arrow diagram right here. And one really easy way to tell if you're dealing with a function or not on an arrow diagram is just look at all the vectors. Look at all the arrows. I'm just going to focus on the arrows. Do you see any arrows that are coming out of one number? So there's only one arrow coming out of here. There's only one arrow coming out of 2. There's only one arrow coming out of 4, one arrow out of 5, and etc. And so, yeah, that is a function for sure. And so if I list out the domain, if I put those in order, we have 3, it looks like it's already in order. -3, 2, 4, 5, and 11. And the range is all the y values. So 8, 9, 10, and 11. So some people say, well, how come that's a function if there's 2 arrows pointing at 9? And that's okay. Remember, it's got to be one member of the domain relates to exactly one member of the range, and that's still true. 2 is only relating to 9. 4 is only relating to 9. So those are 2 different points on a graph. Okay, now moving on to the vertical line test for identifying functions, which is a really easy way, again, visually to tell whether something's a function or not. And the definition that I have written down is that if a vertical line can be drawn anywhere, just anywhere, and let's say you just draw it in one place. I mean, you can really draw it in anywhere you want on the coordinate plane, but if you can draw it anywhere, not just cherry picking like a certain spot, but anywhere on the coordinate plane, and it only goes through the graph, whatever's drawn on the coordinate plane, if it only goes through the graph at one single point, then it is a function. So the vertical line test is a very easy thing you can do. Just draw a vertical line anywhere, and if it goes through the graph at one point, then that's a function. So that right there passes the vertical line test. I can draw a vertical line over here. It passes the vertical line test there. So I could draw a vertical line anywhere, a straight up and down line, and it only goes through my graph at one point. That is a function. Okay, right here we have an ellipse that is drawn, and if we draw a vertical line right here, you're going to notice, okay, well, it goes through that graph, that goes through that ellipse right there and right there, and that goes through 2 points. That is not a function. Goes through those 2 points right there. And some people will always say, well, hold up, Mr. Oliver, What if I draw a vertical line right here? It passes the vertical line test because it only goes through 1 point. And I'll say, yeah, you're right, it only goes through 1 point. But the vertical line test has to work anywhere on the graph, and it doesn't work here, nor does it work here. You can't just cherry pick it, like I said. You can't just go, well, it works right here. Or some people will, they'll do this. Let me just kind of take away some of these points. But they'll just do this. They'll say, well, it passes the vertical line test there. And I'll say, yeah, you only have 1 point, but a line has to go forever in both directions. So you just can't draw a line segment. It's not a vertical line segment test. It's a vertical line test. So it does not pass. So that would be not a function. Is it a relation? Absolutely. But not just because it's not a function. Both those graphs were a relation. Okay, now moving on to steps to determine whether a function, whether y is a function of x given an equation. This is kind of what I was talking about at the beginning, which is, x is your independent value, it's your independent variable, and y is your dependent variable. And we want to see, is it indeed, is y a function of x? And one way you can kind of test this is just by putting in some values. Right? Let's say if x equals 1, then we're going to get, well, y equals 3 times 1 plus 3. And then that's going to be y equals 3 plus 3, y equals 6. Okay, well, let's say x is equal to 2. So I'm going to get y times 3 times 2 plus 3. Well, y equals 6 plus 3, so y equals 9. Let's say x equals 0. 3 times 0 plus 3, well, 3 times 0 is 0, and 0 plus 3 is 3. So that looks like, yeah, that definitely seems to work. Because every time we put in a 1, I didn't get something different for y. There's only one example where I can put a 1 in and I get out a 6. There's no other example like that where it's going to come out that way. If I put in a 2, 2 is independent of 9. So this would be a yes. So now if you really look at number 7 here, and your initial impressions might tell you, you know what, it looks like y is the independent variable and x is your dependent variable. And you can just test out your hypothesis by putting in some values here. Let's say I put in some y values. Let's say I say y is 2. All right, well, if I put that in there, I'm going to get 2 squared equals 4 times x. And let's just see what happens here. So 2 times 2 is 4 equals 4x. And if I solve this, I get x equals 1. That works out that way. All right, let's say I put in y equals negative 2. Let's try that out. Let's say we do that. So if I put in negative 2 for y, and I do negative 2 squared equals 4x, well, negative 2 squared is 4, and then I get 4 equals 4x, and I get the same outcome because I'm going to divide by 4, and then I get x equals 1. Now look, this doesn't make any sense right here. I've got the same x value, but I have totally different y values. I have totally different y values. When I put in x, I get a 1. When I put in an x of 1, I get y equals 2. And also when I put in x as 1, I get a y out as negative 2. So this is a perfect example of where this is not an example of where the y is dependent on the x. That's an example of where the x is dependent on the y, and that's not how functions work. Now in number 8 is a little tricky because again, it's set up like number 7, but let's look at how this works. Let's say we make x equal to 2. Well then, that makes 1/2 equal to y. Let's say I make x equal to 3. Then 1/3 equals y. So it seems like, if I make x 4, then that's going to equal y, so 1/4. So it seems like I'm getting a definite relationship here where y is dependent on x. However, there are some limitations here because there is a number, if you guys can remember back to when we were talking about constraints of a possible equation, you might notice that we can never have what number in the denominator, and that's going to be a 0. So if I put x as 0, well, that's not going to work. So I could put yes. I mean, this is kind of a yes and but. So yes. Okay, so this is something we've talked about before too in class, which is, the procedure for finding the domain given an equation. You might want to ask yourself, okay, is there anything that x cannot be? That's a really simple question, but it can be a little bit tricky. But there's a lot of things that x could be, but there might be only a few things that x cannot be. So if you can figure out what that one or what those two things are, perhaps, that x cannot be, then you're going to figure out what the domain is. Because if you know what it cannot be, then you know what it can be. It's a definite relationship right there. Okay, now this is an example of one where x could be absolutely anything. So the domain can be all real numbers. Okay, for example, 11 here, this is where you want to be careful. And I think we've discussed this too. But in the denominator, you do not want the denominator to equal 0. You don't want 5 over 0. That's undefined. That's not going to happen. So what can x be so that it makes 0? Well, if we solve that equation right there, if I just move the x over to the other side, well, I get 12 equals x. If I put this in set notation, or if I put this in interval notation, so the domain is all real numbers as long as x does not equal 12. For number 12, the domain can be anything as long as x does not equal 0, because we're multiplying 5 times x. So if you do 5 times 0, then yeah, that's going to stick a 0 in the denominator, which is not a good thing. That's going to be undefined. But as long as x is anything else, it could be a negative number, it could be a positive number, it could be a fraction, it could be a decimal. But as long as it's not 0 itself, then it is not. Then it is a member of the domain. Number 13 is an example of where the domain is going to be all reals. It can absolutely be anything. It could even be 0. Okay, for number 14, let's look at what's going on here and what can x not be. Now this is a little bit different because the x or the y term is squared. So you might want to look at it. Let's look at it from this direction. Let's look at it as y squared equals x and see how that works. Let's say y is equal to 5. Well, what's 5 squared? Well, that's going to be 25. Well, let's say y is negative 5. Well, that's going to be positive 25 as well. All right, let's say y is equal to 3. Well, 3 squared equals x. Well, that equals 9. Let's say it's negative 3. Well, negative 3 squared is also 9. So I'm getting that. Now, what do you notice that x cannot be? Is x ever going to be negative? No, there's no way of ever doing this where x is going to be negative. Is there ever going to be an example of where you take y and multiply by y and get a negative x? So the domain is all values of x greater than or equal to 0. So let's go ahead and start off here where it says how to evaluate functions and function notation. Let's get into function notation, which is, you might see a function notation like this, where you'll have like f of x. Now that just means the function of x. You'll sometimes see that referred to as the f of x, the function of x. So the function of x is, and I know I'm going to get a little bit confusing here, but f of x, even though it has an x in it, is technically just your y. That's what it is. So don't confuse the f of x with being an x. It's actually just the y. Okay, so let's get down to evaluating. So right here, this is real straightforward evaluating one where you just have to put in 3 where there's an x. So you just have to put 3 in there. So you got 4 times 3 minus 1. 4 times 3 is 12. 12 minus 1 is 11. So y equals 11 on that one. On the next one, this is one where it's more in function notation. And we've got if f of x equals 4x minus 1, find the f of 3. Now this just means the function of 3. the function of 3, that just means put the 3 in for x. That's all you got to do. So it's just like the above question. It's just written kind of in a different way. But you're going to just do 4 times 3 minus 1, again, which is 12 minus 1, which is 11. So the function of 3 equals 11. That's how you'd write your answer. The f of x is equal to 11. So f of 3 is equal to 11. Same thing right here. We're going to put in, right here, we're going to figure out what the function of negative 6 is. So we're going to put in, all right, f of x equals 2 times negative 6 plus 10, and then negative 6 times 2 is negative 12, and negative 12 plus 10 is negative 2. So there it is. So your function of negative 6 is negative 2. We're basically just saying that y equals, I should have said that before, but we're just essentially saying that y equals negative 2 when x equals negative 6. I know function notation can be a little bit weird. Now, function notation is not always using the letter f. Sometimes you'll see g, sometimes you'll see h, and I think that's just because it's next to the letter f. I'm not sure otherwise why they use those letters, but I usually see f, g, and h quite often for function notation. But just like we were doing before, we're going to find the g function of 8. So that means we're going to put that 8 in where we see an x. Okay, so I got 77 there. So the g of 8, I think that looks more like a parentheses, is 77. That's it. Okay, for the next example here, it says find the function of 3 for each equation. So I'm going to look at those equations. Where does the x equal 3? Where does the x equal 3? And then I'm going to write down what the corresponding y value is to that number. So let's say, all right, I've got a 3 right here, and that corresponds to 12. So there you have it. So the function of 3 for number 19 is 12. Number 20, the function of 3, there's a vector pointing to negative 1. So there you have it. The function of 3 for number 20 is negative 1. On a graph, on a coordinate plane, we're looking at our x value. So here's 3. All right, but then I'm going to look, okay, where does that correspond to on the graph? And right there is where 3 is on the graph. Now, what y value does that correspond to? So that corresponds to a 4. So the function on this graph, on this linear equation right here, the function of 3 is equal to 4. All right, and kind of just talking about this even further, this was not part of the question, but let's say I said, what's the function of negative 1? What's the function of negative 1 according to this problem? Well, we're going to find x, find where x is equal to negative 1, and find the corresponding y value. So there's where x is equal to negative 1, and that corresponds to negative 4. All right, what's the function of 0? What's the function of 0? Well, here's 0 on the x, and that corresponds to right there. So that equals negative 2. So that's all we're doing there. Now this next example right here, we've got the function of h is equal to negative 3x plus 1. And so now we want to figure out, okay, what's the h of m? These are super abstract, but you're just doing some basic algebra right here. So we're just going to put in the m value. We're going to put the m value in for x. That's all we got to do for this one. So the h of m is going to be negative 3 times m plus 1. That seems too easy. Sometimes in math, if something seems too easy, and you're not doing it right. But this is one of those examples where, yeah, it is that easy. That's it. All right. For this example right here, we're putting in w plus 5 into the x coordinate. So this one's going to take a little bit more work. So in place of x, we're putting in w plus 5. So I don't want to just leave it like that. I want to distribute. So negative 3 times w, and negative 3 times 5 is negative 15, plus 1, and then clean it up some more. You get negative 3w minus 14. So there you have it. So the h of w plus 5, I should use the right notation, is equal to negative 3w minus 14. So that would be the correct notation that you would use. Now, a linear function just has, we've talked about linear graphs and linear equations. Linear functions just mean it makes a line. It's not a parabola, it doesn't curve at all, but it makes a line. And all we have to do for this one right here is just graph it, all right? And this equation, I know it's written in function notation, but if that throws you off, just write it like this: y equals 1/3 x minus 2. And the same things that are true for graphing are the same thing for function. There's your slope. Your slope is 1 to 3, up 1 over 3. And there's your y-intercept at -2. So I'm going to start with my y-intercept. And then my function is up 1 over 3. So I'm going to go up 1 over 3. 1, 2, 3. I'm going to put a point there. And I'm going to go down 1, left 3 to get me another point. So there's the f of x. All right, so for number 25, we've got a compact disc. A CD is read at 44.1 kilohertz, which means that it scans 44,100 samples per second, samples of sound per second on the CD to produce the sound that we hear. I think that's pretty typical for a CD. So the function s of t, so s is samples of sound, equals 44,100 times t, tells us how many samples of sound, s to t, the function of s to t, are read in t seconds. Okay, so the first example right here, how many samples of sound are read in 30 seconds? So for that one, we're going to look at the s of 30, and we're going to put that in there, 44,100 times 30. All right, so when you put this all in, the s of 30 is going to equal, looks like a 6. The s of 30 is going to equal 1,323,000 samples of sound in 30 seconds. Okay, for this next one right here, it says how many samples of sound are read in 2 minutes. So just make sure that we convert 2 minutes to seconds. 2 minutes is going to be what, like 1,000 seconds or something? No, it's 60 times 2, which is 120. So you're going to do basically the same thing. So the s of 120 is going to equal 44,100 times t. So we're just going to do the same thing, 44,100 times 60 this time around. So for that one, I get s of 120 equals 2,646,000 samples of sound in just 2 minutes. Okay, for example C here, we want to kind of go the different route here, which says how long will it take the CD player to scan over 3 million samples of sound? So this time around, we're not going to put in 3,087,000 where the t is. This time we're going to use the equation. We're going to use the equation 44,100 t equals s of t. But this time we're going to put this number in that spot right there. So we're going to solve it like a typical equation here. And then we're just going to divide both sides by 44,100. And this is one of those questions, of course, where you probably want to use your calculator for this. All right, so when you break this down, you get t is equal to 70 seconds. Now, if you really want to be super precise with that, you could just write that as 1 minute and 10 seconds. Okay, that does it for your lesson. Everyone have a great day, and I'll see you next time around.